Hello, friend. Welcome to a journey through distances so vast they'll make your mind quiet, in the best possible way. Tonight, imagine this. You're standing in a field under a sky full of stars. You point to one, a bright one twinkling softly against the darkness. Someone asks you, "How far away is that?" And you answer, 4 light years. They nod as if they understand. But here's the truth. Neither of you really does. Because a light year isn't just a number. It's a distance so enormous, so incomprehensibly vast, that even saying it out loud feels like speaking a language the human brain was never designed to process. 4 light years. What does that even mean? It sounds almost poetic, doesn't it? Like something you could touch, something you could imagine. But you can't. None of us can. And that's exactly what makes it beautiful and terrifying. If you're finding a strange comfort in that thought, if the idea of cosmic distances both humbles and soothes you, then stay with me. And if this kind of gentle science storytelling helps you drift into deeper thoughts or deeper sleep, consider liking this video and subscribing. It tells me you want more of these quiet journeys through the universe. No pressure, just if it feels right. Now, let's begin at the beginning. Let's talk about what a light year actually is. Most people hear light year and think it's a measurement of time. It's not. It's a measurement of distance, the distance light travels in 1 year. And light, as you probably know, moves fast, really fast. It travels at 186,282 miles per second. That's 7.5 times around the Earth in 1 second. In 1 year, 365.25 days, light covers approximately 5.88 trillion miles. Or if you prefer the metric system, about 9.46 trillion kilometers. Let me say that again. 9.46 trillion kilometers. That's 1 light year. Now, your brain probably just skipped over those numbers. Mine does too. Because we're not built to understand trillion. We're built to understand things we can see, touch, walk to. Our ancestors survived by judging distances they could cross in a day, not distances that take photons a year to traverse. So when I say 946 trillion kilometers, what your brain probably hears is just very far. And honestly, that's fair. But let me try to give you something to hold on to, even if it's just for a moment. Imagine the Earth shrunk down to the size of a single grain of sand. Just 1 grain. Now picture 1 light year stretched out in front of you. If Earth is a grain of sand, 1 light year would be longer than the distance from New York City to Tokyo, multiplied by 170,000. Think about that. The flight from New York to Tokyo is about 600-700 miles and takes around 14 hours. Now imagine making that journey 170,000 times in a row. You still wouldn't have traveled 1 light year. And here's the thing. Most of the stars you see at night, they're multiple light years away. Proxima Centauri, our nearest stellar neighbor, is 4.24 light years away. Sirius, that brilliant star you might spot on a winter evening, is 8.6 light years distant. The North Star Polaris, the one sailors used to navigate for centuries, is 323 light years away. When you look at Polaris tonight, you're seeing light that left that star in the year 1702. That's the era of Isaac Newton, of early Enlightenment Europe, of the first newspapers in America. That light has been traveling through space for over 3 centuries just to reach your eyes. But I'm getting ahead of myself. Let's go back. Back to when humans first started to realize just how far away the stars really were. For most of history, people thought the stars were close, really close. Ancient Greeks believed they were fixed to a crystalline sphere just beyond the planets, maybe a few thousand miles up. Even the great astronomer Tycho Brahe, working in the late 1500s, tried to measure the distance to stars using parallax, the apparent shift in position when you view something from two different angles. He failed, not because he wasn't brilliant, but because the stars are so far away that their parallax shifts are impossibly tiny, far smaller than the instruments of his time could detect. The first breakthrough came from an unlikely place, the moons of Jupiter. In 1676, a Danish astronomer named Ole Rømer was studying Io, one of Jupiter's moons. He noticed something strange. When Earth was moving toward Jupiter in its orbit, Io's eclipses happened earlier than predicted. When Earth was moving away, they happened later. Rømer realized this wasn't because Io's orbit was changing. It was because light took time to travel across space. When Earth was farther from Jupiter, the light from Io had a longer journey, so it arrived later. Rømer calculated that light took about 22 minutes to cross the diameter of Earth's orbit. He was close. We now know it takes about 16 minutes and 40 seconds. But the important thing is this: for the first time, someone had proven that light wasn't instantaneous. It traveled. It had a speed. And if it had a speed, then the distances in space could be measured, if you were patient enough. But measuring the distance to a star that would take another 162 years. In 1838, a German astronomer named Friedrich Wilhelm Bessel finally did it. He measured the parallax of a star called 61 Cygni, a faint star in the constellation Cygnus the Swan. By observing it from opposite sides of Earth's orbit 6 months apart, he detected a tiny shift in its position against the more distant background stars. The shift was minuscule, less than 1 arcsecond, which is 1/30 of a degree. But it was there, and from that shift, Bessel calculated the distance 11.4 light years. Think about what that means. For thousands of years, humans looked up at stars and wondered, are they nearby? Are they distant? Are they even real? Or just holes in the sky? And then in 1838, we finally knew. The stars weren't close. They were almost unimaginably far. So far that their light took over a decade to reach us. So far that the fastest travelers we could build, ships, trains, eventually rockets, wouldn't even make a dent in the journey. And here's where the human mind starts to falter. Because we can say 11.4 light years. We can write it down. We can calculate it. But can we really understand it? Let me give you one more comparison, and then I'll let your mind rest for a moment. Voyager 1 is the fastest human-made object ever launched. It's been traveling since 1977, moving at about 38,000 miles per hour, roughly 17 kilometers per second. It's now over 15 billion miles from Earth, farther than any spacecraft has ever gone. It's in interstellar space beyond the influence of our sun's solar wind. And yet, if Voyager 1 were headed toward Proxima Centauri, which it's not, but let's imagine it would take about 73,000 years to get there. 73,000 years. That's longer than all of recorded human history. That's longer than we've had agriculture, longer than we've had cities, or writing, or mathematics. If Voyager 1 had launched when our species first started painting on cave walls, it still wouldn't be there yet. and Proxima Centauri. That's our closest neighbor. The next nearest stars, Alpha Centauri A and B, are about the same distance. After that, Barnard's star at nearly 6 light-years, Sirius at 8.6, Wolf 359 at 7.9. These are the stars in our immediate neighborhood, cosmically speaking, and none of them are reachable within a human lifetime. Not even close. This is where the mistake happens, the mistake we all make when we first hear the term light year. We hear it and we think, okay, that's far, but it's just a unit of measurement, like a mile but bigger. And technically, yes. But psychologically, no. Because when you say a mile, you can picture it. You've walked a mile. You've driven a mile. You know what a mile feels like. But a light year? You haven't experienced it. You can't experience it. No human ever has. No human ever will. And that's the paradox. We measure light years with precision. We calculate them, map them, catalog millions of stars and galaxies by their distances in light years. But we don't feel them. We can't. Our brains simply don't have the wiring for it. Psychologists call this scope neglect or scale insensitivity. It's the reason why when you hear about a tragedy affecting 100 people versus 10,000 people, your emotional response isn't actually 100 times different. Your brain compresses large numbers into a vague sense of a lot. And the same thing happens with cosmic distances. 1 light year, 1,000 light years, 1,000,000 light years. They all blur into the same overwhelming sense of far. But here's what I find quietly comforting about that. The vastness doesn't need to be understood. It just needs to be acknowledged. You don't have to wrap your mind around 9.46 trillion kilometers. You just have to sit with the feeling that the universe is bigger than you, older than you, stranger than you. And somehow, in that acceptance, there's peace. Because when you look up at the night sky and see a star, let's say it's Betelgeuse, that reddish supergiant in the shoulder of Orion, you're not just seeing a distant sun. You're seeing light that left that star 548 years ago. That light began its journey in the year 1477, when Leonardo da Vinci was painting, when the printing press was still new, when Europeans hadn't yet reached the Americas. That photon, that tiny packet of energy, traveled through the emptiness of space for over 5 centuries just to land on your retina. And in that moment, you're touching the past. You're connected to a time you never lived in a place you'll never go through. Nothing but light. That's what a light year really is. It's not just distance. It's time. It's history. It's memory written in starlight. So when someone asks you, how far is that star? And you say, 4 light years? What you're really saying is this. That star is so far away that its light takes 4 years to reach me. When I look at it tonight, I'm seeing what it looked like 4 years ago. I'm not seeing it as it is. I'm seeing it as it was. And if that star exploded tomorrow, you wouldn't know for 4 years. The star could already be gone, and you'd still see it shining a ghost in the sky, a memory of something that no longer exists. This is the strange, beautiful, unsettling truth of the cosmos. We live in a universe where distance and time are tangled together, where looking out into space means looking back into the past, where the present moment, the true now, is something we can never actually see when we look at the stars. And as we move deeper into this exploration, as we trace the history of how humans learned to measure these impossible distances, you'll start to see that every new discovery didn't just expand our knowledge, it expanded our loneliness. It reminded us how small we are, how brief our lives are, how the universe operates on scales that make our entire existence feel like a blink. But maybe, just maybe, that's exactly what makes it worth exploring. Because in understanding how far the stars are, we also understand how remarkable it is that we can see them at all, that we can measure them, that we can sit here on this small planet with our fragile minds and short lives and still reach out across billions of miles with nothing but curiosity and light. The stars are far, impossibly far. But tonight, they're here with us, and so are you. And that's enough. Let's keep going. Because the story of how we learned to see across such distances, it's just as extraordinary as the distances themselves. For thousands of years, humans looked up at the night sky and saw beauty. They saw patterns. They saw gods and heroes and stories written in starlight. But they didn't see distance. Not really. Because how could they? The stars looked like tiny points of light, all seemingly the same distance away, as if they were painted on the inside of a great dome, just beyond reach. The ancient Greeks called this dome the celestial sphere. They imagined it rotating around the earth, carrying the stars with it. And for a long time, that was enough. The stars were far, yes, but not impossibly far. Maybe a few thousand miles up. Maybe just beyond the moon. Close enough that distance didn't really matter. But then something shifted. Slowly, over centuries, humans began to suspect that the universe was much, much larger than anyone had imagined, and the journey to prove it, that journey was filled with failures, brilliant mistakes and breakthroughs, so profound they changed not just astronomy, but our entire understanding of where we are. Let me take you back to the 2nd century BC to a Greek astronomer named Hipparchus. He's often called the father of trigonometry, and he did something remarkable for his time. He created a catalog of over 850 stars, noting their positions with impressive precision. But more importantly, Hipparchus understood parallax. Parallax is simple in concept. Hold your finger up in front of your face. Close one eye, then the other. Notice how your finger seems to shift against the background. That's parallax. The closer an object is, the bigger the shift. The farther away, the smaller. Hipparchus realized that if you could measure the parallax of a star, the tiny shift in its position, when viewed from different points in Earth's orbit, you could calculate its distance. He tried. He failed. The stars were too far away. Their parallax shifts were too small for the instruments of his era to detect. But the idea was planted. Distance could be measured if only we had the right tools, the right precision, the right patience. Fast forward nearly 2,000 years to the late 1500s. Tycho Brahe, a Danish nobleman with a metal nose, he lost part of his real nose in a duel over mathematics, which tells you something about the man built the most advanced observatory of his time. His instruments were massive, incredibly precise for the era, capable of measuring angles to within a fraction of a degree. Tycho was obsessed with accuracy. He observed the planets, the moon, the stars, night after night, recording their positions with meticulous care. And he too tried to measure stellar parallax. He believed that if the Earth truly orbited the Sun, as Copernicus had suggested, then the stars should show a measurable shift over the course of a year. 6 months apart, Earth would be on opposite sides of its orbit about 186 million miles apart. Surely from such different vantage points, the nearby stars would appear to move against the more distant background stars. Tycho measured, he calculated, he searched, and he found nothing. No parallax. No shift. The stars appeared completely fixed no matter where Earth was in its orbit. So Tycho drew a conclusion. Either the stars were unimaginably far away so far that their parallax was too tiny to measure, or the Earth didn't move at all. And because the first option seemed absurd to him, because distances that vast seemed incompatible with a universe created for humanity, he rejected the Copernican model. He created his own system, a compromise, where the planets orbited the sun, but the sun orbited the Earth. He was wrong, of course. But his failure wasn't foolish. It was honest. He couldn't measure what his instruments weren't capable of seeing, and the truth that the nearest stars were light years away with parallax shifts of less than 1 arcsecond was simply beyond the technology of his time. But Tycho's failure taught the astronomers who came after him something crucial. The stars weren't just far. They were so far that even our best efforts to measure them would require tools, methods, and patience beyond anything yet imagined. Then in 1729, something unexpected happened. An English astronomer named James Bradley was trying to measure stellar parallax just like Tycho. He was observing a star called Gamma Draconis, watching it carefully over the course of a year. And he noticed something strange. The star did shift position, but not in the way parallax predicted. It shifted in the wrong direction at the wrong time. Bradley was confused at first, but then he realized what he was seeing: stellar aberration. It wasn't the star moving. It was the Earth. As Earth traveled around the sun, its motion combined with the motion of incoming starlight, causing the apparent position of stars to shift slightly, like how rain seems to slant toward you when you're driving, even if it's falling straight down. This was huge. Bradley's discovery didn't give him the distance to the stars, but it did something almost as important. It proved conclusively that the Earth was moving. It was observational evidence for the heliocentric model, written in the light of the stars themselves. And it confirmed something else light had a finite speed. Bradley could even use his measurements to calculate that speed, arriving at a value remarkably close to what we know today. But still, no distances. Not yet. The breakthrough finally came in 1838, and it came from 3 astronomers working independently almost simultaneously, as if the universe had decided it was finally time to reveal its secrets. Friedrich Wilhelm Bessel in Germany measured the parallax of 61 Cygni. Thomas Henderson in South Africa measured Alpha Centauri, and Friedrich Struve in Russia measured Vega. All 3 used the same principle Hipparchus had imagined over 2,000 years earlier: observe a star from opposite sides of Earth's orbit, measure the tiny shift, calculate the distance. And it worked. The shifts were minuscule, less than 1 arcsecond, which is 1/3600th of a degree, smaller than the width of a human hair seen from across a football field. But they were there, and for the first time in human history, we had actual measurements, real distances to the stars. Bessel's 61 Cygni, 11.4 light-years, Henderson's Alpha Centauri, 4.37 light-years, Struve's Vega, 25 light-years. Imagine the feeling in that moment. For all of human history, the stars had been mysteries unreachable, unknowable. And suddenly, in 1838, 3 men proved that we could measure them. We could know how far they were, not with mythology or philosophy, but with mathematics and observation and patience. But here's the thing that often gets overlooked. These first measurements opened a door, but they also revealed just how limited our view was. Because parallax only works for relatively nearby stars. Once you get beyond about 1,000 light years, the parallax shift becomes so tiny that even modern telescopes struggle to measure it accurately. For the vast majority of stars in our galaxy, let alone other galaxies, parallax alone isn't enough. So astronomers needed new methods, new tools, new ladders to climb higher into the cosmos. And that's exactly what they built. In 1908, a woman named Henrietta Swan Leavitt was working at Harvard College Observatory. She wasn't a professor. Women weren't allowed to be professors there at the time. She was hired as a human calculator, tasked with analyzing photographic plates of stars. Her job was considered menial repetitive. She was paid 30 cents an hour. But Henrietta Leavitt was brilliant, and she noticed something extraordinary. She was studying a type of star called Cepheid variable stars that brighten and dim in a regular pulsing rhythm. Some pulsed every few days, some every few weeks. Leavitt was looking at Cepheids in the small Magellanic Cloud, a small galaxy near our own. And because all those stars were roughly the same distance from Earth, since they were all in the same galaxy, she could compare their brightness directly. And she found a pattern. The Cepheids that pulsed more slowly were intrinsically brighter. The relationship was precise, predictable, mathematical. If you measured how fast a Cepheid pulsed, you could calculate its true brightness. And if you knew its true brightness and measured how bright it appeared from Earth, you could calculate its distance. This was revolutionary. It meant that Cepheid variables could be used as standard candles, cosmic lighthouses whose true brightness was known. Find a Cepheid in a distant galaxy, measure its pulse, and you could calculate how far away that galaxy was, even if it was millions of light years away, far beyond the reach of parallax. Henrietta Leavitt published her findings in 1912. She received almost no recognition during her lifetime. She died in 1921, never knowing that her discovery would become one of the most important tools in all of astronomy. Because a decade after her death, an astronomer named Edwin Hubble used Leavitt's period luminosity relationship to measure the distance to the Andromeda galaxy. And in doing so, he proved that Andromeda wasn't a nebula inside our Milky Way, as most astronomers believed. It was a separate galaxy over 2 million light years away. The universe once again had grown unimaginably larger, and this became the pattern. Every new method of measuring distance parallax Cepheids, another type of variable star called R Lyrae, the Tully fissure, relation for spiral galaxies, type Ia supernovae. For the farthest reaches, each one extended our cosmic measuring tape a little farther. Each one relied on the method before it, like rungs on a ladder stretching toward infinity. Astronomers call it the cosmic distance ladder. And it's not a solid, certain thing. It's built on assumptions, calibrations, careful observations, and, yes, uncertainties. Each rung depends on the one below it. If you make a mistake early on, that error propagates upward, compounding as you climb. In 1920, there was a famous debate, the Great Debate, between two astronomers, Harlow Shapley and Heber Curtis, about the size of the Milky Way and the nature of spiral nebulae. Shapley argued the Milky Way was enormous, maybe 300,000 light years across, and that the spiral nebulae were just gas clouds within it. Curtis argued the Milky Way was smaller, and the spirals were separate galaxies far beyond. Both were partially wrong. The Milky Way turned out to be about 100,000 light years across, smaller than Shapley thought, but still vast. And Curtis was right about the spirals being separate galaxies, but even he underestimated the distances involved. The point is getting cosmic distances right is hard. It requires building layer upon layer of measurements, each one checked and rechecked, refined, over decades. And even today, with satellites and supercomputers and telescopes in space, there are still uncertainties. We still argue over the exact rate of the universe's expansion, the precise distances to faraway galaxies, the true scale of the cosmos. But here's what I find beautiful about that science isn't about knowing everything with absolute certainty. It's about reducing uncertainty step by step. It's about building a ladder into the unknown and climbing it. Even knowing some rungs might be shaky, because the view from higher up is worth the risk. And the view we've gained, it's staggering. We now know the universe is at least 93 billion light years across. We can measure galaxies billions of light years away. We can trace the light from stars that died before the Earth even formed. But it all started with Hipparchus holding up his hand to the sky and wondering if the stars might shift just a little, if only he could measure carefully enough. It started with Tycho, failing to find parallax, but refusing to give up on precision. It started with Bradley noticing something strange and following it to a truth he didn't expect. It started with Bessel squinting through a telescope at a faint star, and finally seeing the universe move. And it started with Henrietta Leavitt, a woman paid 30 cents an hour, who looked at thousands of stars and saw a pattern no one else had noticed. A pattern that would unlock distances beyond imagining. This is how humans learned to see across light years, not with one grand discovery, but with centuries of patience, failure, brilliance, and stubborn curiosity. Each generation built on the last. Each method extended our reach a little farther. And the lesson in that, it's the same lesson the stars have been teaching us all along. The universe doesn't reveal itself all at once. You have to earn each new piece of knowledge. You have to climb rung by rung, mistake by mistake, toward understanding. The climb is worth it. Because every new measurement, every new method, every new rung on the ladder brings us closer to comprehending the true scale of the cosmos. And in that comprehension, however incomplete, however uncertain, there's a kind of grace. We live in a universe measured in light years. And the fact that we can measure it at all with our small minds and brief lives is perhaps the most extraordinary thing about us. Now, understanding how we measure these distances is one thing, but there's something else we need to talk about. Something that cuts to the heart of why light years feel so impossible to grasp. It's not just that the numbers are big. It's that our brains aren't wired to process them. And when we really try to imagine crossing a light year, traveling to even the nearest star, we run headfirst into the limits of human perception itself. Here's a question that might keep you awake or help you drift off depending on how your mind works. If you could board a spaceship right now and travel to the nearest star at the fastest speed humans have ever achieved, how long would it take? A year? 10 years? A lifetime? Try 73 modern years. 73,000 years to reach a star that's only 4.24 light years away. And that assumes you're traveling at the speed of Voyager 1, the fastest object we've ever launched into space. 3 generations wouldn't be enough. 300 generations wouldn't be enough. You'd need nearly 4,000 generations of humans, born and dying aboard that ship, before anyone saw Proxima Centauri up close. And that's our nearest neighbor. That's the closest star to our sun. Imagine trying to visit anything farther. This is the human scale paradox. We can measure light years. We can calculate them precisely down to the kilometer. We can say with confidence that Proxima Centauri is 24 light years away, that Barnard's star is 5.96, that Wolf 359 is 7.86. We can map these distances, plot them on charts, visualize them in computer simulations, but we cannot truly feel them. Our brains simply don't have the architecture for it. And there's a reason for that. A reason rooted deep in our evolutionary history. For hundreds of thousands of years, humans lived in a world where the farthest distance that mattered was maybe a few hundred miles. That was as far as you could walk in a lifetime, as far as you needed to understand, to survive. Your brain evolved to judge distances you could see, touch, reach. Can I throw this stone and hit that animal? Is that cliff too far to jump? How many days' walk is it to the next valley? Those are the scales our minds are built for. Human scales. Tangible scales. Distances measured in steps and days in the span of a human life. But light years exist on a scale so far beyond human experience that when we encounter them, our brains do something interesting. They give up. Not consciously, not deliberately, but they stop trying to process the actual magnitude and instead compress everything into a vague category of very far. Psychologists have studied this phenomenon extensively. It's called scope neglect, or scale insensitivity, and it shows up in fascinating ways. In one famous experiment, people were asked how much they'd be willing to donate to save birds from drowning in oil spills. One group was told 2,000 birds were at risk. Another group was told 20,000. A third group was told 200,000. You'd expect people to offer 10 times more for 20,000 birds than for 2,000, right? And 100 times more for 200,000. But they didn't. The average donation was roughly the same across all 3 groups, because once the numbers got large enough, people's brains stopped differentiating 2,000 birds, 20,000 birds, 200,000 birds. It all became a lot of birds. The same thing happens with cosmic distances. 1 light year, 1,000 light years, 1,000,000 light years. Your emotional response to these numbers is probably almost identical. They all just feel far. Impossibly far. And your brain, having no framework for distinguishing between them, treats them as essentially equivalent. But they're not equivalent. Not even close. Let me try to give you something to anchor to. Let's start with Proxima Centauri again, because it's the closest and therefore the easiest to think about, though easy is a very relative term here. Proxima Centauri is 4.24 light years away. That's about 25 trillion miles. If you wanted to drive there in a car going 60 miles per hour, never stopping, never slowing down, it would take you about 47 million years. If you walked at a steady pace of 3 miles per hour, it would take 950 million years longer than complex life has existed on Earth. Now, let's say we don't walk. Let's use our fastest spacecraft. Voyager 1, as I mentioned, is moving at about 38,000 miles per hour. That sounds fast. It is fast. But at that speed, reaching Proxima Centauri would still take 73,000 years. The pyramids of Egypt are only about 4,500 years old. The oldest known human settlements are around 12,000 years old. Agriculture itself is only about 10,000 years old. So if we had launched Voyager 1 toward Proxima Centauri, back when humans were still hunter-gatherers, just beginning to settle in one place and plant crops, it still wouldn't be halfway there yet. And that's just Proxima Centauri. Let's look at the next nearest stars. Alpha Centauri, A and B, a binary star system that Proxima orbits at a distance, are also about 4.37 light-years away. So same travel time, give or take. After that, you have Barnard Star at 5.96 light-years. Then Wolf 359 at 7.86 light-years. Lalande 21185 at 8.29 light-years. Sirius. That brilliant star you can see in the winter sky is 8.6 light-years away. If Voyager 1 were headed towards Sirius, which it's not, it would take about 141,000 years to get there. That's longer than Homo sapiens has existed as a species. By the time the ship arrived, we might not even be human anymore. Evolution could have changed us into something else entirely. And here's where the mistake happens. The mistake we all make when we first try to wrap our minds around interstellar distances. We think of space travel the way we think of air travel. You buy a ticket, you board a plane, you sit for a few hours, you arrive. Even the longest flights, New York to Singapore, 18 hours, feel manageable. Uncomfortable maybe, but finite. Human scale. But space doesn't work that way. Space operates on scales so vast that even our fastest technologies are barely crawling. And not just our current technologies, even our most optimistic future technologies. Let's imagine for a moment that we could build a spaceship capable of traveling at 10% the speed of light. That's wildly optimistic, far beyond anything we can currently build. But let's say we figured it out. At 10% light speed, you could reach Proxima Centauri in about 42 years. That's within a human lifetime. A person could leave Earth as a young adult and arrive at Proxima before they died. But here's the catch. Accelerating a spacecraft to 10% light speed would require energy on a scale we can barely imagine. We're talking about energies comparable to detonating thousands of nuclear bombs just to push a single ship up to speed. And then you'd need to slow down when you got there, which requires just as much energy. And you'd need to carry fuel life support shielding from radiation, everything a crew would need to survive for 4 decades in the cold vacuum of space. It's theoretically possible. But practically, we're nowhere close, not even in the same galaxy. Of close, if you'll pardon the pun. Now, let's push the numbers even farther, because Proxima Centauri is actually a best-case scenario. It's close, cosmically speaking. But what if you wanted to visit something more interesting? What if you wanted to see a planetary system we know has Earth-like worlds? TRAPPIST-1, for example. It's a star system about 39 light-years away, and it has 7 Earth-sized planets, 3 of which might be in the habitable zone. It made headlines a few years ago because it's one of the most promising places to search for life beyond Earth. 39 light-years doesn't sound that bad, right? At Voyager 1's speed, it would take 685,000 years to get there. Even at 10% the speed of light, it would take 390 years. You'd need a generation ship, a vessel designed to support multiple generations of people, born and dying, in space, passing the mission down like an inheritance until their distant descendants finally arrived at a world their great, 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 great grandparents had set out to explore. Can you imagine that? Can you imagine boarding a ship, knowing that you will never see the destination, that your children won't see it, that your grandchildren won't see it, that only your descendants, 10 or 15 generations removed, will finally arrive? That's what interstellar travel actually looks like when you do the math. And it gets worse, because most of the stars we can see with the naked eye, the ones that make up the familiar constellations, the ones humans have been looking at and naming and telling stories about for millennia, are hundreds or thousands of light years away. Betelgeuse, that red supergiant in Orion's shoulder, 548 light years. At Voyager speed, you're looking at 9.5 million years. Rigel, the bright blue star in Orion's foot, 860 light years. Deneb, one of the brightest stars in the summer sky, about 2,600 light years. Even at the speed of light itself, it would take 2,600 years to get there. This is what I mean by the human scale paradox. We can see these stars. We can point at them. We can photograph them, analyze their spectra, measure their temperatures and masses and ages. We know more about some distant stars than we know about the deepest parts of our own oceans. But we cannot visit them. Not in any practical sense. Not in any time frame that aligns with human life, human ambition, human patience. And this creates a strange kind of loneliness, doesn't it? We're surrounded by neighbors, billions of stars in our galaxy alone. But we're so far from all of them that we might as well be alone. We can see them. We can study them. We can even send messages toward them, radio signals traveling at the speed of light, carrying greetings from Earth. But we'll never hear back within our lifetimes. The nearest star is 4.24 light years away, which means a radio message would take 4.24 years to get there, and another 4.24 years for a reply to come back. That's 8.5 years for a single exchange, and that's the closest one. Most stars, you'd be waiting centuries or millennia for a reply. This is the paradox. This is why light years feel impossible. Not because the numbers are abstract, we deal with big numbers all the time, but because they represent distances so vast that they disconnect us from any possibility of physical interaction. We can measure them. We can know them, but we cannot cross them. And here's the really uncomfortable truth. This might never change. Even if we develop technologies far beyond what we have now, even if we figure out fusion propulsion or antimatter drives or some other breakthrough, the speed of light remains an absolute limit. Nothing with mass can reach it. Nothing can exceed it. It's not a technological barrier. It's a law of the universe itself, which means that barring some radical discovery we can't even imagine yet, wormholes, warp drives, physics we don't understand, the stars will always be unreachable within a human lifetime. So why do we measure them? Why do we catalog them, map them, send probes toward them, if we know we'll never get there? Because knowing matters. Because understanding matters. Because even if we can't touch something, can't visit, it can't walk on its surface, we can still reach out to it with light and curiosity. and mathematics, we can still connect to it in some small way across the gulf of space. And maybe that's enough. Maybe it has to be, because the alternative, ignoring the stars, pretending they don't exist, staying locked in our small human-scale bubble, would be a different kind of loneliness. The loneliness of never looking up. The loneliness of never wondering. And humans have never been good at not wondering. So we measure light years even though we can't feel them. We calculate distances we'll never cross. We dream of journeys we'll never take. And in that dreaming, in that reaching toward the unreachable, we become something more than just animals bound by gravity and time. We become a species that looks at the impossible and refuses to look away. But here's something I haven't mentioned yet, something that makes the whole picture even stranger, even more beautiful. Because when you look at a star that's 500 light years away, you're not just seeing something far, you're seeing something old. You're seeing the past, and that changes everything about how we understand the universe and how we understand ourselves within it. When you look up at the night sky, you're not seeing the universe as it is. You're seeing it as it was. Every point of light is a messenger from the past, a photon that's been traveling through space for years, centuries, sometimes millions of years, just to reach your eye at this exact moment. Think about that. The starlight touching your retina right now left its source before you were born. Maybe long before. Maybe before your parents were born, or their parents, or their parents' parents, stretching back through generations. You're not looking at stars. You're looking at memories, ghosts, echoes of light from a universe that no longer exists in the form you're seeing. This is what astronomers call look-back time. And it's one of the most profound truths about how we experience the cosmos. Distance and time are inseparable. To look out into space is to look back into history. Let me show you what I mean with a timeline. A cosmic timeline measured in light. Right now, if you could look at the sun, which you shouldn't, obviously, but if you could, you'd be seeing it as it was 8 minutes and 20 seconds ago. That's how long it takes light to travel the 93 million miles from the sun to Earth. So when you watch a sunrise, you're watching an event that actually happened 8 minutes earlier. If the sun suddenly vanished, just disappeared, you wouldn't know for more than 8 minutes. You'd keep seeing it, keep feeling its warmth, keep living in the light of a star that was already gone. That's unsettling, isn't it? But it's also strangely beautiful, because it means that for those 8 minutes, you'd be living in a kind of grace period, a last gift of light from a sun that no longer exists. Now let's go farther. Look at the moon tonight if it's visible, and you're seeing it as it was 1.3 seconds ago. Not much of a difference. Jupiter. Depending on where it is in its orbit, you're seeing it as it was between 33 and 52 minutes ago. Neptune. The farthest planet from the sun is about 4 light hours away. When you look at Neptune, assuming you have a telescope strong enough, you're seeing it as it was 4 hours in the past, still within the same day, still recent in human terms. But now, let's leave the solar system. Let's look at the stars. Proxima Centauri, our nearest stellar neighbor, is 4.24 light years away. When you look at Proxima Centauri, you're seeing it as it was 4.24 years ago. If you're watching it tonight, in December 2025, you're seeing light that left that star in mid-2021, the year of the COVID-19 pandemic, the year of vaccines and lockdowns and uncertainty. That light has been traveling through empty space ever since crossing trillions of miles just to arrive here now in your eye. And if Proxima Centauri exploded tomorrow, you wouldn't know until 2029. Let's keep going. Sirius, the brightest star in the night sky, is 8.6 light years away. The light you see from Sirius left in 2016, the year of the U.S. presidential election, the year Leonard Cohen and Prince died, the year of Pokemon Go. That's what you're seeing when you look at Sirius 2016 frozen in light. Polaris, the North Star, the one sailors used to navigate for centuries, 323 light years away. When you look at Polaris, you're seeing it as it was in the year 1702. That's the era of Isaac Newton, of early Enlightenment thinkers, of the first daily newspaper in England. That light has been traveling for over 3 centuries, and it's only just now reaching Earth. Imagine that. The photons hitting your eye right now witnessed the world when most people still believed in witchcraft, when hardly anyone could read, when America was still a collection of British colonies. Now, let's go farther. Much farther. Betelgeuse, that red supergiant in Orion's shoulder, is about 548 light years away. When you look at Betelgeuse, you're seeing it as it was in the year 1477. Christopher Columbus was 26 years old and hadn't yet sailed for the Americas. Leonardo da Vinci was 25, just beginning his career as an artist. The printing press had been invented only 22 years earlier. The light you're seeing left Betelgeuse before Europeans knew the Americas existed, before the Renaissance had fully bloomed, before the modern world began. And here's the truly wild part. Betelgeuse is a dying star. It's near the end of its life, sometime in the next 100,000 years. Maybe tomorrow. Maybe in 50,000 years. We don't know. It's going to explode in a supernova. So bright, it'll be visible during the day. It might have already exploded. It could have exploded 500 years ago. And we just don't know yet. Because the light from that explosion is still on its way here, racing through space at 282 miles per second. Not yet arrived. We could look at Betelgeuse tonight and see it shining steady and red and have no idea that it's already dead, that the star we're seeing is a ghost. This happens all the time in astronomy. We see stars that have already died. We see galaxies as they were billions of years ago, long before Earth even existed. We look out into space, and we're looking into a museum of the past, a gallery of light from events that are already over. Let me give you more examples, because this gets even stranger the farther out you go. The Pleiades, the Seven Sisters. That little cluster of stars you might notice in the winter sky is about 144 light years away. When you look at the Pleiades, you're seeing them as they were in 1581. That's when Shakespeare was 17 years old, before he'd written a single play. Before Hamlet, before Romeo and Juliet, before anything. The light that left the Pleiades that year has been traveling through space for 444 years, and it's only now reaching your eyes. The Orion Nebula, that glowing cloud of gas and dust where new stars are being born, is about 344 light years away. Look at the Orion Nebula, and you're seeing it as it was in the year 681 AD. That's the early Middle Ages. The Islamic Golden Age was just beginning. In Europe, it was the time of small kingdoms and Vikings. The University of Bologna, Europe's oldest university, wouldn't be founded for another 400 years. And we're still in our own galactic neighborhood. We haven't even left the Milky Way yet. The Andromeda Galaxy, the nearest large galaxy to our own, is about 2.5 million light-years away. When you look at Andromeda, and if you're somewhere dark enough, you can see it with the naked eye as a faint smudge. You're seeing it as it was 2.5 million years ago. That's long before Homo sapiens existed. That's the time of Australopithecus, our distant ancestors, who were just beginning to walk upright, just starting to use simple stone tools. That light left Andromeda before we were human, before we had language, before we had fire. And now, let's go really far. Let's talk about quasars. Quasars are among the brightest objects in the universe, supermassive black holes at the centers of distant galaxies, consuming matter and spewing out energy. The nearest quasar, 3C273, is about 2.4 billion light-years away. When you look at 3C273, which requires a very powerful telescope, you're seeing it as it was 2.4 billion years ago. That's when Earth was still in the Proterozoic eon. Life existed, but only as single-celled organisms and simple multicellular forms. There were no plants on land, no animals, no trees, no fish, just bacteria and algae floating in ancient oceans. The light from that quasar has been traveling for longer than complex life has existed on Earth. Do you see what this means? Do you see why this is so important? When astronomers look at distant galaxies, they're not just seeing far away. They're seeing far back. They're witnessing the universe as it was billions of years ago, when it was younger, hotter, different in fundamental ways. And by looking at different distances, by arranging galaxies and quasars and stars in order of their look back, time, astronomers can piece together the history of the universe itself. They can watch it evolve, change, grow from the dense hot soup of the early cosmos into the vast, structured web of galaxies we see today. This is cosmic archaeology. We're digging through time, not with shovels, but with telescopes. Every distant star is an artifact. Every galaxy is a fossil. And light is the messenger that carries these fossils to us across billions of years. But here's where people make a mistake. A very common, very understandable mistake. When you hear that a galaxy is 10 billion light-years away, it's easy to think, okay, so I'm seeing it as it was 10 billion years ago. But now, right now, it's still there, 10 billion light-years away, just older. But that's not quite right, because the universe is expanding. Space itself is stretching, and that galaxy, which was 10 billion light-years away when the light left it, is now much farther. The light has been traveling for 10 billion years, but during that time, the space between us and that galaxy has been expanding, pushing it farther away. So now, if you could somehow freeze time and measure the distance right at this instant, the galaxy might be 16 or 17 billion light-years away. But you'll never see it as it is now. You'll only ever see it as it was 10 billion years ago when the light left. And by the time any information from its now reaches you, billions more years will have passed, and it will have changed again. This is the fundamental weirdness of cosmology. There's no universal now. There's no moment in time that applies everywhere in the universe simultaneously. The present moment is local. It exists only where you are. Everywhere else, you're always looking at the past, and this leads to a profound realization. We will never see the universe as it truly is in this moment. we can only ever see a patchwork of different eras all layered on top of each other. The Sun from 8 minutes ago, Sirius from 8.6 years ago, Polaris from 323 years ago, Andromeda from 2.5 million years ago, distant galaxies from billions of years ago. All of it stitched together into a single view of the night sky, like a collage made from photographs taken at wildly different times. You're not looking at one universe. You're looking at trillions of moments in time, all happening at once, all visible simultaneously, but none of them current. It's dizzying, isn't it? It's almost too strange to hold in your mind. But it's true. And it means that the universe you see when you look up at night is not a snapshot. It's a history book, a timeline, a story told in light. And the strangest part, we're part of that story too, because right now, at this very moment, light is leaving Earth and traveling out into space. In 424 years, someone on a planet orbiting Proxima Centauri, if such a person existed, could look at Earth and see us as we are right now. They'd see December 2025. They'd see our cities, our lights, our satellites, and by the time they saw it, we'd already be living in 2029, changed in ways we can't predict. We're all time travelers. Every one of us. We're traveling forward through time at a rate of 1 second per second, and we're leaving a trail of light behind us, a breadcrumb path that stretches out into the cosmos, carrying information about who we were, what we did, what we looked like, moment by moment, year by year. And if someone far enough away could look back at Earth with a powerful enough telescope, they could watch human history unfold. They could see the pyramids being built. They could see Rome rise and fall. They could see the Industrial Revolution, the World Wars, the moon landing. All of it written in light, traveling outward at 186, 282 miles per second, a permanent record of everything we've ever done. But they'd never see us as we are now, only as we were. And by the time they saw us, we might be long gone. This is the gift and the curse of light speed. It connects us across vast distances, but it also separates us in time. It lets us see the universe, but never its present, only its past. And the farther we look, the deeper into the past we see. The farther we reach, the more we realize that everything we're seeing is already over, already changed, already transformed into something else that we won't see for years or centuries or millennia. So when you look at the stars tonight, remember, you're not looking at the universe as it is. You're looking at a universe that no longer exists, except in the light that's only now arriving. You're seeing history. You're seeing memory. You're seeing time itself, frozen and preserved, traveling across the void to meet you exactly where and when you are. And maybe that's why starlight feels so comforting. Because it's patient. It doesn't rush. It just travels year after year, carrying its message from the past, waiting for someone to look up and receive it. The stars aren't just far, they're old. And the farther you look, the older they are. Which means that somewhere out there, written in light, is the entire history of the universe. Not just what happened, but when it happened, preserved in the exact sequence of its unfolding. And we're the only species we know of that can read it, that can look back through time and piece together the story, that can hold billions of years of cosmic history in our minds and try, however imperfectly, to understand. But understanding the distances is one thing. Measuring them is another. And as we've seen, measuring cosmic distances requires something extraordinary: a ladder, a cosmic ladder, built from layer upon layer of observations, each one depending on the one before it, and the story of how we built that ladder. It's a story of genius persistence and the slow, painstaking work of reducing uncertainty, one step at a time. Imagine trying to measure the height of a mountain, but you can't get close to it. You can't climb it. You can't even walk to its base. All you can do is look at it from a distance and try to figure out how tall it is using nothing but geometry, light, and clever reasoning. That's essentially what astronomers have been doing for centuries, except instead of measuring mountains, they're measuring distances to stars and galaxies millions and billions of light years away. And the tool they've built to do this, the cosmic distance ladder, is one of the most ingenious, fragile, and absolutely essential constructions in all of science. It's called a ladder because each measurement technique, each rung, reaches only so far. Once you get beyond its limit, you need a new technique. And that new technique is calibrated using the old one. Each rung depends on the one below it, which means if you make a mistake early on, if one of the lower rungs is wrong, that error propagates upward, getting bigger and bigger the higher you climb. It's a ladder built on assumptions, approximations, and careful calibrations. And yet, somehow, it works. It's allowed us to map the universe from our solar system to the edge of the observable cosmos. But the story of how we built it, that's a story of brilliant people making mistakes, correcting them, and slowly, very slowly, reducing the uncertainty. Let me walk you through it, rung by rung. The first rung is the easiest, at least conceptually. It's called radar ranging, and it's used to measure distances within our solar system. The idea is simple: bounce a radio wave off a planet or moon. Measure how long it takes to come back. And since you know the speed of light, you can calculate the distance. We've done this with Venus, Mars, Mercury, even asteroids. It's precise, reliable, and it gives us a solid foundation for everything that comes next. But radar only works within the solar system. Radio waves get too weak to detect once you go beyond a few light hours. So for anything farther for stars, we need a different method. That's where the second rung comes in: parallax. We talked about this earlier. It's the apparent shift in a star's position when you observe it from opposite sides of Earth's orbit 6 months apart. The closer the star, the bigger the shift. The farther the star, the smaller the shift. Parallax works beautifully for nearby stars, up to a few hundred light years away, maybe 1,000 if you're using really precise instruments. The European Space Agency's Gaia satellite, launched in 2013, has measured the parallax of over 1 billion stars with extraordinary accuracy. It's created the most detailed 3D map of our galaxy ever made. But beyond about 10,000 light years, even Gaia struggles. The parallax shifts become so tiny, fractions of a millionth second, that they're almost impossible to measure reliably. So for anything farther, we need a new technique. Enter the third rung, spectroscopic parallax. Despite the name, it has nothing to do with actual parallax. Instead, it's based on the idea that stars of the same type have roughly the same intrinsic brightness. If you can figure out what type of star you're looking at by analyzing its light, its spectrum, you can estimate how bright it should be. Then, by comparing that to how bright it appears from Earth, you can calculate how far away it must be. It's less precise than geometric parallax, but it extends our reach to tens of thousands of light years, enough to map large portions of the Milky Way. But what about beyond our galaxy? What about measuring the distance to Andromeda, or to galaxies millions of light years away? This is where the ladder gets truly ingenious and truly fragile, because the next rung depends on a discovery made by a woman who was paid 30 cents an hour and never received the recognition she deserved during her lifetime. Henrietta Swan Leavitt. We mentioned her earlier. In 1912, she published her findings on Cepheid variable stars that pulse in brightness with a regular rhythm. And she discovered that the period of the pulse, how long it takes to go from bright to dim and back again, is directly related to the star's intrinsic brightness. The longer the period, the brighter the star. This was revolutionary, because if you find a Cepheid variable in a distant galaxy, you can measure its period, calculate its true brightness, and then by comparing that to how bright it appears, figure out how far away the galaxy is. Cepheid variables became standard candles, cosmic lighthouses, and they extended our reach to millions of light years. In 1923, Edwin Hubble used Leavitt's period luminosity relationship to measure the distance to the Andromeda galaxy. He found Cepheids in Andromeda, measured their periods, and calculated that Andromeda was about 900,000 light years away. That number turned out to be wrong. Andromeda is actually about 2.5 million light years away, but the method was sound. And more importantly, it proved that Andromeda wasn't a nebula inside our Milky Way. It was a separate galaxy. The universe, once again, had grown vastly larger. But here's the thing about the cosmic distance ladder. Every time you add a new rung, you introduce new uncertainties. Cepheids are great, but they're not perfect. There are different types of Cepheids, and they don't all follow the exact same period luminosity relationship. You have to calibrate carefully. You have to check your assumptions. And if you get it wrong, everything above that rung becomes suspect. This is exactly what happened in the Great Debate of 1920, a famous argument between two astronomers, Harlow Shapley and Heber Curtis, about the size of the Milky Way and the nature of spiral nebulae. Shapley believed the Milky Way was enormous, about 300,000 light years across, based on his measurements of globular clusters using RR Lyrae variable stars, which are similar to Cepheids. He also believed the spiral nebulae were small gas clouds within our galaxy. Curtis, on the other hand, thought the Milky Way was smaller and that the spirals were separate galaxies far beyond. Both were partially wrong. Shapley had overestimated the size of the Milky Way. It's actually about 100,000 light years across, because he didn't account for interstellar dust, which absorbed some of the light from distant stars and made them appear dimmer and therefore farther than they really were. Curtis was right about the spirals being separate galaxies, but even he underestimated the distances involved. The point is, cosmic distances are hard, really hard. Even brilliant astronomers using the best methods available can be off by a factor of 2 or 3. And when you're building a ladder where each rung depends on the one below, a mistake at one level ripples upward, compounding the error. This is why astronomers are obsessed with calibration. Every new rung of the ladder has to be carefully tied to the rungs below it. You measure Cepheids in nearby galaxies where you can also measure parallax, so you can check that the Cepheid method gives you the right answer. Then, you use those calibrated Cepheids to measure distances to farther galaxies, and so on up the ladder. But Cepheids only get you so far, maybe 50 or 60 million light years at most. Beyond that, they're too faint to detect, even with powerful telescopes. So we need yet another rung. That's where the Tully-Fisher relation comes in. Discovered in 1977 by astronomers Brent Tully and Richard Fisher, it's based on the observation that for spiral galaxies, there's a relationship between how fast the galaxy is rotating and how bright it is. The faster the rotation, the more massive the galaxy, and the more luminous. Measure the rotation speed, which you can do by looking at the Doppler shift of light from different parts of the galaxy, and you can estimate the galaxy's intrinsic brightness. Then, compare that to how bright it appears and calculate the distance. It's less precise than Cepheids, but it works for galaxies hundreds of millions of light years away. And then, for the farthest reaches of the universe, we have type Ia supernovae. These are exploding white dwarf stars, and they're incredibly useful because they all explode with roughly the same intrinsic brightness. That makes them perfect standard candles. Find a type Ia supernova in a distant galaxy. Measure how bright it appears, and you can calculate how far away the galaxy is. Type Ia supernovae are so bright they can be seen billions of light years away. They've been used to measure the expansion rate of the universe, to discover dark energy, to map the large-scale structure of the cosmos. They're the highest, farthest-reaching rung on the ladder. But, and this is crucial, they're still calibrated using the rungs below them. Astronomers measure type Ia supernovae in nearby galaxies, where they can also measure Cepheids to make sure the supernova method is accurate. And those Cepheids are calibrated using parallax, and parallax is calibrated using radar ranging within the solar system. It all connects. Every rung supports the one above it. The whole structure is interdependent. And that means if you make a mistake anywhere in the ladder, the consequences ripple outward. If your radar measurements are slightly off, your parallax distances will be slightly off. If your parallax distances are wrong, your Cepheid calibrations will be wrong. If your Cepheids are wrong, your measurements of distant galaxies will be wrong. And so on all the way up. This is why astronomers argue so much about cosmic distances. It's why there are ongoing debates about the exact value of the Hubble constant, the rate at which the universe is expanding. Different methods give slightly different answers, and those differences matter. They could mean we're missing something fundamental about how the universe works. But here's what I find beautiful about the cosmic distance ladder. It's not a sign of failure. It's a sign of honesty. Science isn't about pretending you know everything with absolute certainty. It's about building the best model you can with the tools you have and then constantly testing it, refining it, checking it against new observations. The ladder isn't perfect. It's built on approximations, assumptions, careful calibrations. But it works. It's allowed us to measure distances from a few light minutes the distance to the sun, all the way out to billions of light years, to galaxies near the edge of the observable universe. And every rung on that ladder was built by someone. By Hipparchus imagining parallax 2,000 years ago. By Ole Rumor timing the eclipses of Jupiter's moons. by Henrietta Leavitt, paid 30 cents an hour, discovering the key to measuring galaxies. By Edwin Hubble, standing in the cold night air at the Mount Wilson Observatory, looking at photographic plates and realizing the universe was bigger than anyone had dreamed. Each generation built on the work of the one before. Each new technique extended our reach a little farther. And together, over centuries, we've constructed a ladder that stretches from Earth to the edge of the cosmos. But the ladder isn't finished. We're still refining it, still checking it, still climbing higher. And every now and then, we find a discrepancy, a measurement that doesn't quite fit a rung that seems shaky, and we have to go back down, recheck our work, recalibrate. Because that's the lesson of the cosmic distance ladder. Knowledge isn't a destination. It's a process. A slow, careful, painstaking process of reducing uncertainty, one step at a time. And the irony is, the more we learn, the more we realize how much we still don't know. The more precisely we measure cosmic distances, the more questions we uncover. Why do different methods for measuring the Hubble constant give different answers? What role does dark energy play in the expansion of the universe? Are there systematic errors we haven't accounted for? These aren't failures. They're invitations. They're the universe saying, "You're getting closer, but you're not there yet. Keep climbing." And we do. We keep climbing because even if the ladder is fragile, even if it's built on assumptions and approximations, even if every rung is just a little bit uncertain, it's still the best tool we have. It's still the only way we can reach out across the vastness of space and measure the universe. So, when someone tells you a galaxy is 10 billion light years away, know that behind that number is a ladder. A cosmic ladder built by generations of astronomers, each one adding a rung, each one extending our reach a little farther. It's not a guess. It's not a wild estimate. It's a carefully constructed chain of measurements, each one checked against the others, each one calibrated and refined. It's imperfect, but it's ours. And it's one of the most remarkable things our species has ever built. Now we've talked about measuring light years. We've talked about how to build a ladder to reach across cosmic distances. But there's something we haven't addressed yet. Something fundamental, because all of these measurements, all of these numbers, 100 light years, 1,000,000 light years, 10 billion light years, they're just numbers. And as we've seen, the human brain doesn't really process big numbers the way it should. 1,000, 1,000,000, 1,000,000,000, they all just blur into a lot. And that creates a problem. Because when numbers lose their meaning, when distances become so vast that our minds can't hold them, how do we even think about the universe? How do we navigate a cosmos measured in scales our brains were never designed to comprehend? Here's a strange experiment. Close your eyes for a moment and try to imagine 1 light year. Really imagine it. Not as an abstract number, 9.46 trillion kilometers, but as an actual distance. You could visualize, feel, comprehend. Can you do it? Can you hold that distance in your mind, the way you can hold the distance from your house to the grocery store, or from New York to Los Angeles? Probably not. And here's the stranger part. Now try to imagine 1,000 light years, then 1,000,000, then 1,000,000,000. Does each one feel proportionally bigger, or do they all just collapse into the same vague sense of incomprehensibly far? If they all feel roughly the same, you're not alone. Because when numbers get large enough, when they exceed the scale of human experience, our brains stop processing them as meaningful quantities. They all become equally incomprehensible. And that creates a profound problem when we're trying to understand a universe measured in distances our minds were never designed to grasp. Psychologists call this phenomenon number numbness, or psychophysical numbing. And it explains why most people have essentially the same emotional reaction to a tragedy affecting 100 people as they do to one affecting 100,000 people. The numbers are different by a factor of 1,000, but our emotional response barely changes. Our brains compress large numbers into categories: a few, many, a lot, and then just too many to really process. The same thing happens with cosmic distances. 1 light year, 1,000 light years, 1,000,000 light years intellectually. You know they're different. But viscerally, emotionally, perceptually, they might as well be the same. They're all just far. Let me show you what I mean with some real examples. The Milky Way galaxy. Our home galaxy is about 100,000 light years in diameter. If you're sitting near the edge, as we are the center of the galaxy, is roughly 26,000 light years away. That's the distance light travels in 26,000 years. The light you'd see from the galactic core, left there during the last ice age, when woolly mammoths still roamed the earth, when Neanderthals were still alive in Europe. Now, the local group, the collection of galaxies that includes the Milky Way Andromeda and about 50 smaller galaxies, spans roughly 10 million light years. That's 100 times bigger than the Milky Way. The light from the far edge of the local group left when Earth was in the Miocene epoch, when early apes were just beginning to evolve, long before anything resembling a human existed. Now, the Virgo supercluster, the larger structure that contains the local group and thousands of other galaxies, spans about 110 million light years. That's more than 1,000 times bigger than the Milky Way. The light from the far edge of the Virgo supercluster left during the Cretaceous period, when dinosaurs still ruled the Earth about 45 million years before the asteroid impact that would wipe them out. And the observable universe, the portion of the universe we can see, it's about 93 billion light years in diameter. Now be honest with yourself. Did those numbers feel different? Did 100,000 light years feel distinctly smaller than 10 million, which felt distinctly smaller than 110 million, which felt distinctly smaller than 93 billion? Or did they all just blur into really, really big? If they blurred, that's normal. That's your brain doing what it's designed to do, which is to categorize things that are beyond the scale of survival-relevant experience into a single bucket labeled not relevant to daily life. But here's the problem. When we're trying to understand the cosmos, these differences matter enormously. The difference between 100,000 light years and 93 billion light years isn't trivial. It's the difference between crossing a single galaxy and crossing the entire observable universe. But our brains treat them almost identically. So what do we do about this? How do astronomers deal with numbers so large that even thinking about them clearly becomes difficult? They cheat in the most brilliant way possible. Instead of using linear scales where each step is the same size, they use logarithmic scales, where each step is a multiplication, not an addition. Think about it like this. On a linear scale, you might go 1, 2, 3, 4, 5. Each number is one more than the last, but on a logarithmic scale, you go 1, 10, 100, 1,000, 10,000. Each number is 10 times the previous one. Why does this help? Because it matches how our brains actually process large numbers. We don't perceive the difference between 1 million and 2 million the same way we perceive the difference between 1 and 2. But we do perceive the difference between 1 million and 10 million, roughly the same way we perceive the difference between 1 and 10. Logarithmic scales compress enormous ranges into manageable ones, and that's why astronomers use them constantly. Take the magnitude scale for measuring star brightness. It was invented by the ancient Greek astronomer Hipparchus around 120 BC, and it's logarithmic. A star of magnitude 1 is about 2.5 times brighter than a star of magnitude 2, which is 2.5 times brighter than magnitude 3, and so on. So a magnitude 1 star is about 100 times brighter than a magnitude 6 star. The scale compresses a huge range of brightness into a simple set of numbers between 1 and 6 for naked eye stars, and it extends into negative numbers for the very brightest objects. The sun is magnitude 26.7. The full moon is 12.6. Venus, at its brightest, is about 4. The scale feels natural because it matches how we perceive brightness. Doubling the actual brightness doesn't make something look twice as bright to our eyes. Our perception is logarithmic. Distance scales work the same way. Instead of light years, professional astronomers often use parsecs, and even more often, they use kiloparsecs and megaparsecs. 1 parsec is about 3.26 light years. It's the distance at which one astronomical unit, the distance from Earth to the Sun, subtends an angle of 1 arc second. It's a geometrically defined unit tied directly to the method of parallax, which is where the name comes from, parallax of 1 arcsecond. A kiloparsec is 1,000 parsecs, or about 3,260 light years. A megaparsec is 1,000,000 parsecs, or about 3.26 million light years. And when you're talking about the large-scale structure of the universe, distances are often given in megaparsecs, not light years, because it makes the numbers more manageable. The Virgo cluster is about 16.5 megaparsecs away. The Coma cluster is about 100 megaparsecs away. The Hubble constant, the rate at which the universe is expanding, is measured in kilometers per second per megaparsec. These units don't make the distances smaller, but they make them easier to work with, easier to compare, easier to think about without your brain shutting down. But even with logarithmic scales, even with units like megaparsecs, there's still a fundamental problem. We can't feel these distances. We can't anchor them to anything in our lived experience. So let me try a different approach. Let me try to give you something to hold on to, not by making the universe smaller, but by making you understand just how strange it is to live in a universe where scale matters this much. Here's a thought experiment. Imagine you could shrink the observable universe down so that the Earth was the size of a single atom, a hydrogen atom, the smallest, simplest atom. How big would the observable universe be at that scale? It would be about 13 light years across, roughly the distance to the nearest dozen or so stars. Let that sink in. If you compressed the entire observable universe 93 billion light years down so that Earth was the size of an atom, the universe would still be bigger than the distance to our nearest stellar neighbors. Or try this. Imagine you're an ant, and you're trying to understand the size of the Earth. You can crawl around your anthill. You can maybe explore a few square meters of ground. But the Earth is huge. It's 75 kilometers in circumference. To an ant, that's incomprehensible. The ant can't walk around the Earth. It can't even conceive of distances that large. Now humans trying to understand the scale of the universe, we're the ants. The universe is 93 billion light years across, and we're sitting on a planet 12,742 kilometers in diameter, trying to wrap our minds around distances that are quintillions of times larger than anything in our experience. We're not equipped for this. We're not built for this. Our brains evolved to track antelope across a savanna, to judge the distance to a cliff, to navigate forests and rivers, not to comprehend the distance to a quasar 10 billion light years away. And yet, somehow, we've managed to do it. Not by feeling the distances, but by building tools, mathematics logarithms, calibrated measurement techniques that let us think about them indirectly. But here's the cost. We lose the visceral sense of scale. We lose the gut-level understanding of just how big these numbers really are. 1,000,000 light years, 1,000,000,000 light years, they become abstract. They become just numbers on a page, coordinates on a map. And that's a loss. Because part of what makes the universe awe-inspiring is its scale, the sheer, overwhelming, incomprehensible vastness of it. And if we treat light years like we treat miles or kilometers, just another unit, just another measurement, we miss that. So how do we get it back? How do we reconnect with the enormity of cosmic distances without getting lost in number numbness? One way is through comparison. Not just abstract comparisons, but personal ones. Think about the fastest you've ever traveled. Maybe 500 miles per hour in an airplane. At that speed, it would take you about 6.7 million years to travel 1 light year. So if you wanted to visit Proxima Centauri 4, 24 light years away, you'd need to fly continuously for 28.4 million years at 500 miles per hour without stopping. Or think about your lifetime. Let's say you live 80 years. That's about 2.5 billion seconds. Light travels 186,282 miles in 1 second. So in your entire lifetime, every second from birth to death, light travels about 466 billion miles. That's not even 1/10 of a light year. Not even close. In your entire life, light will travel less distance than separates us from even the nearest star. And here's another one. Think about human history. All of recorded history from the earliest writing in Mesopotamia around 3200 BC to now is about 5,125 years. In that time, the entire span of civilization light has traveled 5,225 light years. That's enough to reach maybe 200,000 stars if they were all equally spaced. But the Milky Way contains between 100 and 400 billion stars. So in all of human history, light from our sun has reached only a tiny, tiny fraction of our galaxy. Most of the stars in the Milky Way don't even know we exist yet, because the light carrying information about our solar system hasn't reached them. We are in a very real sense invisible to most of the universe. Not because we're small, though we are, but because the universe is so large and light is so slow that information about us simply hasn't had time to propagate very far. And this brings up one of the strangest aspects of cosmic distances. They're not just spatial. They're temporal. They're informational. They're limits on what can be known, what can be seen, what can be influenced. If a civilization on a planet 10,000 light years away looked at Earth with a powerful telescope, they wouldn't see us. They see Earth as it was 10,000 years ago. They'd see a planet covered in ice with early human societies just beginning to develop agriculture. They'd have no idea we'd built cities, invented writing, split the atom, gone to the moon, and we wouldn't know about them either. If they'd built a civilization 5,000 years ago, cities, technology, maybe even space travel, we wouldn't see it for another 5,000 years. This is the tyranny of the light speed limit. It doesn't just make travel slow. It makes knowledge slow. It makes the universe a place where vast distances separate not just locations, but entire timelines, entire epochs, entire histories that unfold in isolation, because the light carrying information about them hasn't arrived yet. So, when we talk about light years, we're not just talking about distance. We're talking about isolation. We're talking about the fundamental loneliness of existence in a universe so vast that even traveling at the speed of light, the fastest possible speed, you'd still be cut off from most of it. And maybe that's why numbers lose meaning when we talk about cosmic distances. Because the numbers aren't the point. The point is the feeling of being small, the feeling of being temporary, the feeling of being part of something so much larger than yourself that even your fastest thoughts, your brightest ideas, your most powerful technologies can't reach across it. The universe is big, incomprehensibly big, and no amount of logarithmic scaling, no cleverness with units, no mathematical tricks can change that. We can measure it. We can map it. We can build models and simulations and visualizations, but we can't shrink it down to human scale. We can't make it comfortable. We can't make it comprehensible. And maybe we're not supposed to. Maybe the vastness is the lesson. Maybe the incomprehensibility is the point. Maybe the universe is trying to teach us something about humility, about patience, about the limits of what minds like ours, brilliant as they are, can truly hold. But if there's one thing that makes the vastness bearable, it's this. We're not trying to cross it. We're not trying to visit every star map, every galaxy catalog, every corner of the cosmos. We're just trying to understand it, to see it, to know that it's there. And for that, we don't need to conquer distance. We just need light. Because light crosses those distances for us. Light travels from the farthest galaxies across billions of light years and arrives here at our telescopes, carrying information, carrying stories, carrying history. And when we capture that light, when we analyze it and study it and piece together what it's telling us, we're not just doing science. We're listening. We're hearing the universe speak in the only language it knows, the language of photons, wavelengths, redshifts, spectra. The universe is vast, but it's not silent. And as long as we're willing to listen, as long as we're patient enough to wait for the light to arrive, we're never truly alone. But there's something we haven't talked about yet, something even stranger than the vastness of space. Because light doesn't just travel through space, it travels through time. And the speed of light isn't just a limit on how fast we can go. It's a limit on how fast information can travel, how fast causality can propagate, how fast anything in the universe can influence anything else. And that limit shapes everything about how the cosmos works. Imagine you're standing in a field at night looking up at Betelgeuse, that brilliant red star in Orion's shoulder. It's 548 light years away, and let's say that right at this moment, right now, it explodes in a supernova. a catastrophic stellar death, one of the most violent events in the universe, releasing more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. How long until you know about it? How long until that information, the fact that Betelgeuse has died, reaches you 548 years? 548 years, because that's how long it takes light to travel from Betelgeuse to Earth. And light traveling at 186,282 miles per second is the fastest way information can move through the universe. Nothing can go faster. Not a signal, not a message, not a particle, not even the force of gravity itself. This is the speed limit of knowledge. And it's one of the most profound, strangest, and most unsettling truths about the cosmos. Because it means that when we talk about cosmic distances, we're not just talking about space. We're talking about time. We're talking about how long it takes for anything at all, to influence anything else. The speed of light isn't just a speed. It's the speed of causality. It's the rate at which causes propagate to effects, at which information travels, at which one part of the universe can know about another part. And this has consequences. Deep, strange, beautiful, lonely consequences. Let me take you back to 1905. A young patent clerk in Switzerland named Albert Einstein published a paper that changed everything. It was called On the Electrodynamics of Moving Bodies, and buried in its mathematics was a revolutionary idea. The speed of light is the same for everyone, no matter how fast they're moving. This sounds simple, maybe even obvious, but it's not. It's profoundly strange. Because if you're on a train moving at 100 miles per hour and you throw a ball forward at 50 miles per hour, someone standing on the ground sees the ball moving at 150 miles per hour. The speed of the train plus the speed of the ball. That's how velocities add. That's common sense. But light doesn't work that way. If you're on a spaceship moving at half the speed of light and you shine a flashlight forward, you might expect someone standing still to see that light traveling at 1.5 times the speed of light. But they don't. They see it traveling at exactly the speed of light. The same speed you see, the same speed everyone sees no matter how fast they're moving. This is weird, really weird, and the only way it can be true is if time and space are not absolute, if they're flexible, if they bend and stretch depending on how fast you're moving. Time slows down for you as you go faster. Space contracts, and the speed of light remains constant for everyone always, no matter what. This is special relativity, and one of its most important consequences is this: nothing with mass can reach the speed of light. You can get close, 99% of light. Speed, 99.9%, 99.99%, but you can never reach it. Because as you approach light speed, time slows down for you. Your mass effectively increases, and it takes more and more energy to accelerate even a little bit faster. To actually reach light speed would require infinite energy, which means it's impossible. The speed of light is an absolute cosmic speed limit, not a technological limit, not something we might overcome with better engineering, a fundamental law of the universe. And that means that no matter how advanced we become, no matter what technologies we develop, we will never be able to send information faster than light. We will never be able to travel faster than light. We will never be able to influence anything beyond a certain distance in less than a certain amount of time. This is the speed limit of knowledge, and it shapes everything. Here's an example. Right now, as you're listening to this, the sun is 93 million miles away. If the sun suddenly disappeared, just vanished, how long would it take for you to notice? You might think you'd notice immediately. After all, it would get dark, bright, and cold. The sun's gravity would stop holding Earth in orbit, and we'd start drifting off into space. But none of that would happen immediately, because the information that the sun is gone has to travel from where the sun was to where you are. And that information travels at the speed of light. So for 8 minutes and 20 seconds, you'd see nothing unusual. The sun would still appear to be there, shining as always. You'd still feel its warmth. Earth would still orbit normally held by the sun's gravity. Everything would seem fine. And then, 8 minutes and 20 seconds after the sun vanished, the light would stop. The sky would go dark. The warmth would begin to fade. And at the exact same moment, Earth would stop orbiting and start moving in a straight line because the sun's gravitational pull would cease. Why? At the same moment? Because gravity also propagates at the speed of light. It's not instantaneous. If the sun disappeared, the change in its gravitational field would spread outward as a gravitational wave, moving at exactly the speed of light, taking 8 minutes and 20 seconds to reach Earth. This was Einstein's insight. Gravity isn't a force that acts instantly across space. It's a curvature of space-time that propagates at light speed, and that means that gravitational information, the information that tells a planet how to orbit, that tells space how to bend, can't travel faster than light either. For over a century, this was just theory. Brilliant theory. Yes, confirmed by countless experiments, but still just mathematics and prediction. Until August 17, 2017. On that day, 2 neutron stars, the collapsed cores of dead stars, each about 1.4 times the mass of the sun, but only 12 miles across, collided 130 million light-years away in the galaxy NGC 4993. The collision produced a burst of gravitational waves that rippled through space-time, traveling outward at the speed of light. 1.7 seconds later, those gravitational waves reached Earth. They were detected by LIGO, the Laser Interferometer, Gravitational Wave Observatory, and Virgo, another gravitational wave detector in Europe. The signal lasted about 100 seconds a chirp in space-time as the 2 neutron stars spiraled inward and merged. And then 7 seconds after the gravitational waves arrived, telescopes around the world detected a burst of gamma rays, light, electromagnetic radiation, also traveling at the speed of light. This was huge, because it proved for the first time that gravity and light travel at the same speed. Not approximately the same, exactly the same. The gravitational waves and the light left the collision at the same moment, traveled 130 million light-years across space, and arrived at Earth 1.7 seconds apart, a difference caused not by different speeds, but by slightly different paths through intervening matter and space-time curvature. This confirmed Einstein's prediction. Gravity propagates at the speed of light. Causality propagates at the speed of light. Information propagates at the speed of light. And that means the universe has a built-in delay, a lag, a fundamental separation between cause and effect that grows with distance. If you're talking to someone 10 feet away, the lag is negligible, about 10 nanoseconds, 100 millionth of a second. You don't notice it. But if you're talking to someone on the moon, the lag is 1.3 seconds each way. They say something. You hear it. 1.3 seconds later, you respond. They hear your response. 1.3 seconds after that, it's noticeable. Conversations feel stilted, delayed. If you're communicating with a rover on Mars, the lag is between 4 and 24 minutes, depending on where Mars is in its orbit. You send a command. Wait 4 to 24 minutes for it to arrive. Wait another 4 to 24 minutes for a response. You can't drive the rover in real time. You have to send instructions and hope nothing goes wrong while you're waiting. And if you're trying to communicate with Proxima Centauri, 4.24 light years away, the lag is 4.24 years each way. Send a message. Wait 4.24 years for it to arrive. Wait another 4.24 years for a reply. 8.5 years for a single back and forth. A conversation that takes minutes with someone on Earth would take decades with someone on Proxima Centauri. And for stars farther away, forget it. For most of the stars, you can see with the naked eye hundreds or thousands of light years away. You'd be waiting centuries or millennia for a reply. This is the loneliness of the light speed limit. It doesn't just make travel slow. It makes communication slow. It makes interaction slow. It means that even if there are other civilizations out there, even if they're trying to talk to us, even if they've been broadcasting signals for centuries, we might not have heard them yet because their signals are still on the way. And if we send a reply, they won't hear it for centuries or millennia more. We could be surrounded by neighbors and never know it because the distances are so vast and the speed of light is so slow, cosmically speaking, that we're all isolated in our own bubbles of space-time, separated by years or centuries or millennia of light travel time. But the speed limit of knowledge has an even stranger consequence. It creates something called the cosmic horizon. Here's how it works. The universe is expanding. Space itself is stretching, carrying galaxies away from each other. And the farther away a galaxy is, the faster it's receding. This is Hubble's law, discovered in 1929. The recession velocity of a galaxy is proportional to its distance. Now, here's the key. If a galaxy is far enough away, it's receding faster than the speed of light. Not because it's moving through space faster than light. It's not. Nothing can do that. But because the space between us and that galaxy is expanding so fast that the distance grows faster than light can cross it. And if a galaxy is receding faster than light, then light from that galaxy will never reach us. Ever. No matter how long we wait. Because the light is trying to cross a distance that's growing faster than the light itself can travel. It's like running on a treadmill that's going faster than you can run. You're moving forward, but you're still going backward relative to where you started. This creates a cosmic horizon, a boundary beyond which we can never see, never communicate, never receive information. And because the universe is accelerating in its expansion, driven by something we call dark energy, this horizon is getting closer. Not in distance, but in terms of what we can eventually see. Galaxies that are currently visible to us will eventually cross the horizon. Their light will redshift, stretched by the expansion of space, until it becomes so faint, so stretched, that it disappears entirely. And then, from our perspective, those galaxies will be gone. Not destroyed, not vanished, just unreachable, beyond the boundary of what can ever communicate with us. Right now, the cosmic horizon is about 46.5 billion light years away in all directions. That's the comoving distance, the distance accounting for the expansion of space. Anything beyond that is and will always be invisible to us, not because it's too faint to see, but because the light from it will never arrive. The expansion of space has carried it too far too fast. And here's the uncomfortable truth: this boundary is permanent. Even if we had infinite time, even if we waited trillions of years, we would never see beyond it. Because the universe is expanding faster than light can cross the ever-growing distance. There are parts of the universe we will never know about. Not because we lack the technology, not because we haven't waited long enough, but because the laws of physics, the speed of light, the expansion of space, have placed them forever beyond our reach. This is the ultimate isolation. The universe is not just vast. It's structured in such a way that parts of it are fundamentally unknowable. There could be entire galaxies, entire clusters, entire superclusters of matter out there, and we will never see them, never detect them, never know they exist. And it gets worse. Because the universe is accelerating, the cosmic horizon is shrinking. In the far future, trillions of years from now, all the galaxies beyond our local group will have receded beyond the horizon. Astronomers in that distant era, if they exist, will look up at the night sky and see only the Milky Way and Andromeda and a few small satellite galaxies. They'll have no evidence that the universe is expanding, no evidence of the Big Bang, no evidence that there's anything beyond their small island of galaxies. The universe will have erased its own history, and beings living in that era will have no way of knowing the truth unless they've preserved the knowledge from earlier eras when the evidence was still visible. This is what the speed limit of knowledge means. It's not just a limit on how fast we can travel. It's a limit on what we can know, on what we can see, on what we can ever hope to understand about the universe. And yet, despite this, we keep trying. We keep building bigger telescopes, more sensitive detectors, more clever experiments. We keep searching for signals from other civilizations, even though any reply would take decades or centuries. We keep cataloging galaxies billions of light years away, even knowing that we're seeing them as they were billions of years ago, and that they may have changed beyond recognition, or even ceased to exist in the time it took their light to reach us. Why? Why do we bother when the universe seems designed to keep us isolated, ignorant, separated by distances so vast that even light, the fastest thing there is, takes eons to cross them? Because knowledge matters. Because understanding matters. Because even if we can't visit those distant galaxies, even if we can't talk to civilizations around distant stars, even if parts of the universe are forever beyond our reach, we can still learn. We can still wonder. We can still reach out with our telescopes and our mathematics and our curiosity. The speed limit of knowledge is real, but it's not a wall. It's just a delay, a lag, a reminder that the universe is patient, and we need to be patient too. Light travels at 186,282 miles per second. Gravity propagates at the same speed. Information causality, influence, all of it moves at this cosmic speed limit. And that shapes everything. It shapes how we explore the universe, how we understand time and space, how we think about distance and connection and isolation. But here's the thing: the speed limit doesn't stop us from seeing. It just means we're always seeing the past. And maybe that's fitting. Because when we look at the stars, we're not just seeing light. We're seeing history. We're seeing stories. We're seeing messages from the past written in photons traveling for years or centuries or millennia just to reach us. And sometimes those messages arrive carrying news we're not prepared for. News of stars that have already died, events that are already over light, that's outlived the object that created it. Right now, at this very moment, you could be looking at a star that no longer exists. A star that burned brightly for millions of years, that fused hydrogen into helium in its core, that warmed planets, that perhaps even hosted life, and then died. Exploded, collapsed, extinguished, gone. And yet, you see it shining. Because the light that left that star hundreds or thousands of years ago is still traveling through space, still carrying the image of a star that's already dead, and it won't reach Earth and reveal the truth until long after the star itself has become a ghost. This is one of the strangest truths about the night sky. When you look up, you're not seeing stars as they are. You're seeing them as they were. And some of them, we don't know which ones we can't know, which ones are already gone. Their light is all that remains. A fossil, a memory, an echo traveling through the void. We live in the light of the dead, and we always have, and we always will. Let me show you what I mean. Stars don't live forever. They're born, they live, and they die. The lifetime of a star depends on its mass. Small stars, red dwarfs like Proxima Centauri, can burn for trillions of years, far longer than the current age of the universe. Medium-sized stars like our sun last about 10 billion years. Massive stars, the bright blue giants, burn hot and fast, living only a few million years before they run out of fuel and explode. And when they die in different ways. Small stars fade slowly, cooling into white dwarfs, dense Earth-sized remnants that glow faintly for billions of years before finally going dark. Massive stars go out in violence, exploding as supernovae, briefly outshining entire galaxies before collapsing into neutron stars or black holes. But here's the thing. Whether a star fades or explodes, whether it dies quietly or catastrophically, the light it emitted before its death is still out there, still traveling. And if that star is far enough away, the light from its final moments, or even from long before its death, is still on its way to us. So when we look at distant stars, we're seeing them as they were years, centuries, millennia ago. And some of them are already dead. Let me give you some examples. Real stars, real possibilities. Take Eta Carinae, one of the most massive and unstable stars known. It's about 7,500 light-years away in the southern constellation Carina. Eta Carinae is a stellar monster somewhere between 100 and 150 times the mass of the Sun, and about 5 million times brighter. It's so unstable that in the 1840s, it underwent a massive eruption, becoming the second brightest star in the sky for a brief period before fading again. That eruption ejected enormous amounts of material into space, forming a glowing nebula around the star that we can still see today. Eta Carinae is a ticking time bomb. Astronomers believe it could explode as a supernova at any time, literally any time. It could happen in the next 1,000 years, or the next 100, or it could have already happened 5,000 years ago, and we just don't know yet, because the light from that explosion is still traveling toward us, racing through space at 186,282 miles per second, and it won't arrive for another 2,500 years. When Eta Carinae finally does explode, or when we finally see it explode, it'll be one of the brightest events in the night sky. It might even be visible during the day. For weeks or months, it will outshine everything except the sun and moon. And then it will fade, leaving behind either a neutron star or a black hole and a beautiful expanding shell of gas and dust. But the star itself, it might already be dead, and we just don't know. Or consider WR104, a Wolf-Rayet star about 8,000 light-years away in the constellation Sagittarius. Wolf-Rayet stars are the final stage in the life of very massive stars. They've already burned through most of their hydrogen and helium, and they're now fusing heavier elements in their cores while shedding their outer layers in powerful stellar winds. They're unstable, short-lived, and they end in supernovae. WR104 is particularly interesting and concerning because it's part of a binary system, and as the two stars orbit each other, they create a spiral pattern of gas and dust that looks like a cosmic pinwheel. It's beautiful, but it's also potentially dangerous, because when WR104 explodes, it might produce a gamma-ray burst, a focused beam of extremely high-energy radiation that, if pointed at Earth, could strip away part of our ozone layer and cause mass extinctions. Now, the good news is that WR104 probably isn't pointed directly at us. The bad news is that we're not entirely sure. And even if we were sure, there's another problem. WR104 is 8,000 light-years away. If it exploded 6,000 years ago, during the time when humans were building the first pyramids in Egypt, we wouldn't see the explosion for another 2,000 years. And by the time we saw it, it would be too late to do anything about it. The star could be dead. The gamma-ray burst could already be on its way, and we're living in blissful ignorance, seeing the light of a star that no longer exists. This is the unsettling reality of stellar archaeology. We're not just looking at old light, we're looking at a universe where some of the brightest, most prominent stars we see could already be corpses, their light the only thing left to tell us they ever existed. And we have historical examples of this. Real documented cases where humans witnessed the death of a star, not knowing what they were seeing. In 1054, AD, Chinese and Arab astronomers recorded the sudden appearance of a guest star in the constellation Taurus. It was so bright, it was visible during the day for 23 days, and it remained visible at night for nearly 2 years before fading from view. They had no idea what it was. They just wrote it down as a curiosity, a temporary new star that appeared and then vanished. We know now what they saw, a supernova, the explosion of a massive star about 6,500 light-years away. The explosion happened around the year 4546 BC, during the Neolithic period, when humans were just beginning to develop agriculture and settle in permanent communities. The light from that explosion traveled for 6,500 years, and it finally reached Earth in 1054 AD, when Chinese astronomers looked up and saw what they thought was a new star. But it wasn't new. It was old. Very old. The star had already died thousands of years earlier. The light was just catching up. Today, we can see the remnant of that explosion. It's called the Crab Nebula, a glowing cloud of gas and dust expanding outward at about 1/500 kilometers per second, powered by a rapidly spinning neutron star at its center. The Crab Nebula is one of the most studied objects in astronomy, and it's the grave of a star that died before the pyramids were built, but whose death announcement only arrived 1,000 years ago. Or take Tycho's supernova, observed in 1572 by the Danish astronomer Tycho Brahe. It appeared in the constellation Cassiopeia and was visible for about 18 months. It was bright enough to cast shadows at night, and it challenged the prevailing belief that the heavens were unchanging and eternal. We now know it was a Type Ia supernova, a white dwarf star in a binary system that accumulated too much matter from its companion, became unstable, and exploded. The explosion happened about 8,000 years ago. Around 6,000 BC, the light traveled for 8,000 years, and it reached Earth in 1572, where Tycho saw it and recorded it, not knowing he was witnessing the death of a star that had been dead for millennia. And here's the thing that really unsettles people when they first think about it. The stars we see in the night sky right now, the familiar constellations we've known since childhood. Some of them might be dead already. We don't know which ones. We can't know. But statistically given the distances involved and the lifetimes of different types of stars, it's almost certain that some of the stars visible to the naked eye have already reached the end of their lives. Take Betelgeuse, for example. It's 548 light-years away, and it's a red supergiant nearing the end of its life. When you look at Betelgeuse, you're seeing it as it was in the year 1477. If it exploded in 1600, we wouldn't know until the year 2148. If it exploded in 1800, we wouldn't know until 2348. It could explode next week, or it could have exploded 500 years ago, and we're just waiting for the light to arrive. Astronomers watch Betelgeuse carefully. It's been dimming and brightening irregularly over the past few years, which has led to speculation that it might be getting ready to explode. But the truth is, we don't know. It could explode in the next 100,000 years. It could have already exploded. We just have to wait and see. And when it does explode, when we see it explode, it will be spectacular. Betelgeuse will likely reach a magnitude of around 12, about as bright as the full moon. It will be visible during the day. It will cast shadows at night. And it will remain visible for weeks or months before gradually fading over the course of a year or two. But the star itself, the actual physical star, it might have died centuries ago. The explosion might have already happened. The shockwave might be tearing through the surrounding interstellar medium right now, at this very moment. And we're sitting here, seeing the star shine, living in the light of something that may already be gone. This is the paradox of cosmic distance and the finite speed of light. The universe we see is not the universe as it is. It's a patchwork of different moments in time all stitched together by light that left its source at different eras and is only now arriving. When you look at Sirius 8.6, light-years away, you're seeing 2016. When you look at Arcturus 37 light-years away, you're seeing 1988. When you look at Rigel 860, light-years away, you're seeing the year 1165, the time of the Crusades. And some of those stars, statistically, have probably changed. Some have aged. Some have swelled or shrunk. Some have exploded. We just don't know yet. And here's the really strange part. This applies to everything, not just stars. Galaxies, too. When we look at the Andromeda Galaxy, 2.5 million light-years away, we're seeing it as it was 2.5 million years ago. If something catastrophic happened there 1 million years ago, if a massive black hole devoured a significant portion of the galaxy, If a gamma ray burst sterilized an entire region, we won't know for another 1.5 million years. We're living in a universe where the present is local and everywhere else is the past. And the farther we look, the deeper into the past we see. And the deeper into the past we see, the less we know about what's actually happening right now. If you wanted to know the current state of the universe right now, at this exact moment, you couldn't. You'd have to wait. You'd have to wait for light from distant stars and galaxies to arrive carrying information about what was happening when that light left. And by the time it arrived, it would already be outdated. This is the loneliness of living in the light of the dead. We're surrounded by stars, but we never see them as they are, only as they were. And some of them, we don't know which are ghosts, memories, light without a source. But maybe that's okay. Maybe that's even beautiful, because it means that when we look at the stars, we're not just seeing objects in space. We're seeing history. We're seeing a timeline written in light, stretching back through years and centuries and millennia. We're seeing the universe unfolding one photon at a time, one moment preserved forever in the light that carries it forward. And if a star dies, if it explodes or fades or collapses, its light doesn't die with it. The light keeps going. It keeps traveling. It keeps carrying the memory of that star outward, across the galaxy, across the universe, until it finally arrives somewhere, maybe at a telescope, maybe at an eye, maybe at a consciousness that can look at it and understand what it means. We live in the light of the dead, but that light is not sad. It's not mournful. It's a gift. It's a message from the past, from stars that lived and died long before we were here, and their light has traveled across unimaginable distances just to reach us, just to tell us they existed, just to remind us that the universe is vast and old and full of stories. And maybe in some distant future, long after our sun has died, long after Earth is gone, long after humanity is nothing but a memory, our light will still be traveling. Photons that left Earth millions of years ago will still be crossing the galaxy, carrying images of our cities, our forests, our oceans, our lives. And if someone far away looks at that light, they'll see us, not as we are, as we were, as we are now in this moment, frozen in light, traveling forever. We are all, in a sense, already part of the past. We're already ghosts in someone else's telescope light from a world that may no longer exist by the time our photons arrive. And there's something strangely comforting about that, because it means we're not forgotten. As long as light travels, as long as photons carry information, as long as the universe has eyes to see, we're remembered. Our light, our moment, our existence preserved forever in the cosmic record. But all of this, the dead stars, the old light, the paradox of seeing the past when we look into space, it all brings us back to one final question. A question that ties everything together. Because we've talked about what light years are, how we measure them, why they're incomprehensible, how they isolate us, how they reveal the past. But we haven't talked about what they mean, what it means to live in a universe measured in distances too vast for the human mind to truly grasp. There's a quote by the French philosopher Blaise Pascal, written in 1670, that has haunted me for years. He wrote, "The eternal silence of these infinite spaces frightens me." Pascal was a mathematician, a physicist, a brilliant mind who understood the cosmos better than most people of his era. And yet, when he contemplated the vastness of space, what he felt wasn't wonder. It was fear. Fear of the silence. Fear of the emptiness. Fear of just how small and insignificant we are in the face of infinity. I understand that fear. I think we all do, if we're honest with ourselves. Because when you really think about light years, when you really sit with the idea that the nearest star is 4.24 years away at the speed of light, that most of what we can see is hundreds or thousands or millions of years distant, that the observable universe is 93 billion light years across, and we're sitting on a tiny planet orbiting an ordinary star in a corner of an average galaxy, it's overwhelming. It's humbling in a way that can feel almost crushing. We are so small, so temporary, so limited. A human lifetime is maybe 80 years if we're lucky. The light we can see with our own eyes left its source decades or centuries or millennia ago. The universe has been expanding for 13.8 billion years, and we've been here for the tiniest fraction of that time. We're barely a blink, a flicker, a momentary spike of consciousness in an ocean of time and space that stretches far beyond anything we can comprehend. And light years, those incomprehensible distances, they're a constant reminder of that. They're a reminder that we cannot reach most of what we can see. We cannot visit it. We cannot touch it. We can only observe it from a distance. And even that observation is delayed, filtered through years or centuries of light travel time. So, why do we bother? Why do we measure light years? Why do we build telescopes and spacecraft and detectors? Why do we spend billions of dollars and countless hours trying to understand distances? We'll never cross stars. We'll never visit galaxies. We'll never reach. I think it's because the incomprehensibility is the point. The vastness is the lesson. And what the universe is teaching us isn't that we're small or insignificant. It's that we're part of something much, much larger than ourselves. And that being part of that, being connected to it, even in a tiny way, is enough. Let me explain what I mean. In 1990, the Voyager 1 spacecraft, which had completed its primary mission of exploring Jupiter and Saturn, was about 3.7 billion miles from Earth, on the edge of our solar system, about to enter interstellar space. The astronomer Carl Sagan convinced NASA to turn Voyager's camera around one last time and take a photograph of Earth from that incredible distance. The result was an image that became known as the pale blue dot. In the photograph, Earth appears as a tiny speck, less than a single pixel, suspended in a beam of scattered sunlight. It's barely visible. You have to know where to look to even find it. And Carl Sagan, when he saw that image, wrote something that I think captures the strange beauty of our cosmic situation better than anything else I've ever read. He said, "Look again at that dot. That's here. That's home. That's us. On it. Everyone you love. Everyone you know. Everyone you ever heard. Of every human being who ever was lived out their lives, the aggregate of our joy and suffering. Thousands of confident religions, ideologies, and economic doctrines. Every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species, lived there on a mote of dust suspended in a sunbeam. That photograph was taken from less than 4 billion miles away. Not even a light day. Not even close to a light year. And yet from that distance, Earth, the only home we've ever known, was already invisible except as a pale blue pixel. Now, imagine looking at Earth from Proxima Centauri 424 light-years away. You wouldn't see it at all. Not with the naked eye. Not with most telescopes. Earth would be lost in the glare of the sun, completely invisible, utterly insignificant. And yet, here we are, on that pale blue dot, looking out at the universe, measuring light-years, mapping galaxies, trying to understand our place in the cosmos. And the miracle, the real miracle, isn't that we're significant. It's that we're here at all, that we can look, that we can wonder, that we can build instruments to see farther than our eyes can reach, and mathematics to comprehend distances our brains can't visualize, and stories to make sense of a universe that seems designed to remind us of our own smallness. We live in a universe measured in light years. Distances so vast, they make our minds quiet, our thoughts slow, our sense of self shrink down to something small and humble. And maybe that's exactly what we need. Maybe in a world where we're constantly told we're the center of everything, where our problems feel all-consuming, where our perspectives feel absolute, maybe we need the stars to remind us that we're not the center, that there's something bigger, something older, something that was here long before us and will be here long after we're gone. But here's the thing that doesn't make us meaningless. It makes us miraculous. Because think about what had to happen for you to be here right now, listening to this. The universe had to form 13.8 billion years ago in the Big Bang. Stars had to condense from hydrogen and helium, fuse heavier elements in their cores, and explode as supernovae, scattering carbon and oxygen and nitrogen and iron into space. Those elements had to come together in a cloud of gas and dust that collapsed to form our sun and planets. Earth had to cool. Water had to condense. Life had to emerge from chemistry. That life had to evolve for 3.8 billion years, surviving mass extinctions, ice ages, asteroid impacts, until finally, improbably, it produced a species capable of looking up at the night sky and asking, "How far away are those stars?" You are made of atoms forged in the hearts of dying stars. Every carbon atom in your body, every oxygen molecule you breathe, every calcium atom in your bones. They were created billions of years ago in a supernova explosion scattered across light years of space and eventually gathered here on this planet in you. You're quite literally stardust, conscious stardust. Stardust that can look back at the stars and understand, at least in part, where it came from. And light years, those incomprehensible distances, they're not obstacles. They're connections. They're the threads that link us to the rest of the universe. Because every photon that reaches your eye from a distant star has traveled across light years of empty space just to get here, just to be absorbed by the retina in your eye, just to trigger a cascade of chemical reactions that your brain interprets as light, as color, as beauty. When you look at the stars, you're not separate from them. You're connected to them by light, by history, by the fact that you and they are made of the same material, created in the same processes, part of the same cosmic story. The universe is vast. Light years are incomprehensible. The distances are too great to cross the timescales, too long to grasp the numbers, too large to feel. But we don't need to cross them. We don't need to grasp them. We don't need to feel them. We just need to acknowledge them, to sit with them, to let them remind us that we're part of something bigger than ourselves, something ancient, something beautiful, something that doesn't care about our deadlines or our worries or our plans because it operates on scales of billions of years and billions of light years. And yet somehow, it produced us. It made us. It gave us eyes to see and minds to wonder and hearts that can feel awe when we look up at the night sky. There's a reason we measure light years, even though we can't comprehend them. It's not because we think we'll ever travel those distances. It's because the act of measuring the act of reaching out with our instruments and our mathematics and our curiosity is itself a way of connecting, a way of saying, I see you. I know you're there. I want to understand you, even if I never can fully. And maybe that's the real meaning of light years. They're not just distances. They're invitations. Invitations to wonder, to explore, to reach beyond ourselves, to remember that we're small, yes, but we're not alone. We're surrounded by stars, galaxies, nebulae, black holes, pulsars, quasars, an entire universe of objects and phenomena and mysteries that we're only just beginning to understand. And the fact that we can't visit them, the fact that they're light years away, unreachable within a human lifetime, that doesn't diminish them. It doesn't diminish us. If anything, it makes the act of looking even more profound. Because we're not looking for practical reasons. We're not measuring cosmic distances because we think we'll use them to build a highway to Andromeda. We're looking because we can't help it. Because curiosity is woven into the fabric of what it means to be human. Because even when faced with the incomprehensible, we still want to know. We still want to understand. We still want to measure, to map, to name, to make sense of the cosmos, even knowing that the cosmos is far too big to ever fully make sense of. Blaise Pascal was frightened by the infinite spaces. And I understand that. But I think there's another way to look at it. A way that's not about fear, but about wonder. Yes, the universe is vast. Yes, light years are incomprehensible. Yes, we are small and temporary and limited. But we are also conscious. We are also curious. We are also capable of building telescopes that can see billions of light years into the past, of doing mathematics that can describe the curvature of space-time, of creating models that predict the evolution of galaxies and the birth of stars. We are small, but we are not simple. And the fact that we tiny specks on a tiny planet orbiting an ordinary star in a corner of an average galaxy can look out at the universe and understand even a fraction of it, that's not frightening. That's miraculous. So, the next time you look up at the night sky, remember this. You're not looking at stars. You're looking at light years. You're looking at distances so vast they make your mind quiet. You're looking at photons that have been traveling for years or centuries or millennia just to reach you. You're looking at the past, frozen in light, delivered to you across the incomprehensible emptiness of space. And you're part of it. You're connected to it. Not despite the distance, but because of it. Because the same atoms that make up those distant stars also make up you. Because the same laws of physics that govern the expansion of the universe also govern the beating of your heart. Because you and the cosmos are not separate. You're part of the same unfolding story written in matter and energy and space-time and light. The universe is vast. Light years are incomprehensible. And that's okay. That's more than okay. That's beautiful. Because the vastness isn't something to be conquered. It's something to be felt, to be honored, to be approached with humility and wonder, and a quiet, grateful awareness that we get to be here at all. We live in the light of distant stars. We measure distances we'll never cross. We dream of places we'll never visit. And somehow, in all of that impossibility, in all of that incomprehensibility, we find meaning. We find beauty. We find a reason to keep looking up. And maybe that's the greatest lesson light years can teach us, that understanding doesn't require comprehension. That connection doesn't require proximity. That meaning doesn't require certainty. Sometimes it's enough just to look, to wonder, to let the vastness wash over you like starlight, gentle, patient, infinite. The stars are far, impossibly far. But tonight, they're here with us, and so are you. And that's enough. Thank you for staying with me through this journey across light years and time. I hope it brought you some peace, some wonder, maybe even a little bit of awe at the sheer strangeness and beauty of the universe we inhabit. If this resonated with you, if it helped you drift into deeper thoughts or deeper sleep, I'd be grateful if you'd leave a like or subscribe. It lets me know these quiet explorations of the cosmos are finding the people who need them, and there are more stories to come, more mysteries to explore, more distances to contemplate. The universe is vast, and we've barely scratched the surface. Until then, rest well. Dream of distant stars. And remember, you're made of light, measuring light, living in light. And that's a beautiful way to be. Good night, friend. The stars are waiting.